Okay, so I don't think we'll be here that much longer. I think this will go pretty fast. Now, if you're doing a picture project, you know, with 10 pictures, this is a picture that you might get, something like this, called crepuscular rays. Actually, if you're doing pictures, or even if you're not doing pictures, on the way out to your car tonight, look at the moon, which is foolish. It's gibbous, but kind of around the moon, kind of there's clouds over here. There were just a minute ago. It's kind of got this color sort of thing. That is actually called a, let me get this right, corona, corona, right now. So this is the moon. It's got a kind of a color to it. A corona has some kind of orange, kind of red sort of to it. And what it is that there is water vapor up there making that happen. So that is also something you could put in your picture project. But crepuscular rays kind of look like this. Conditions that you need to get a crepuscular ray going is you need to have some sort of water vapor kind of here. Okay, that's actually kind of giving us our kind of striations. You need to have an irregular object, which could be clouds in this case, or a mountain, and the sun needs to be low on the horizon. So, crepuscular rays. They sound bad, but they're really not. So, the word backscattering, well, I'm not backscattering, but the places that are unshadowed, or the bright places actually are where light is scattering back to the observer. Yeah, something like that. Crepuscular rays, I know that for sure. So, changing gears from albedo to absorption. They both start with the letter A. Ugh. So here, if we talk about kind of absorption of the energy from the sun, in general, the atmosphere, that would be like the air, okay? The atmosphere is not good at, air doesn't absorb, it doesn't absorb thermal energy, it doesn't absorb stuff from the sun very good. About 20% is what the atmosphere absorbs. And then it would re-emit 20%, okay? So that's just the air. But now the geosphere, okay, the Earth's surface is really good. It's, instead of 20, it's 80. So that means that when the sun shines on the Earth, okay, gets to the Earth's surface, the Earth basically sucks up 80% of that energy. And then right away, and even throughout the day, or even throughout the night, I guess I should say, there's like little energy wiggles coming from the Earth's surface. Okay, that's the Earth re-emitting that energy. So it's a good absorber and re-emitter of energy. So I think I probably mentioned that when I said like the troposphere, this layer of air that's next to the Earth, you know, troposphere, stratosphere, mesosphere, thermosphere, that sort of thing. In the troposphere, as you go up, it gets colder because you're getting farther from kind of the Earth's surface. The next figure that we're going to see actually kind of breaks down by gas that's in the atmosphere, how it interacts with radiation coming from the sun. And so what we're going to see is just like you have like a window wide open for the fresh air to come in, or a window closed because it's cold outside, you don't want that cold air to come in. We say that the Earth's atmosphere, like for instance, is open to visible light from the sun. But the Earth's atmosphere, because of some components in the Earth's atmosphere, is closed to, I mentioned, like gamma rays, okay, or harmful radiation. So this says visible light and infrared radiation can kind of come through the Earth's window, atmosphere, can pass pretty well. So here we go. Starting with nitrogen. I know it's hard to see, but clear over here. This actually is the presence of nitrogen. Notice that, let's see, how does this work? This is looking at percent transmittance. So that gas actually transmittance. Absorbs energy, heats. Just a minute. I wonder, it's absorbance. Yeah. See, I don't like, and actually this isn't something I did. This is something your author did. It switched from percent transmittance to, I guess that makes sense. How much for instance, how much does nitrogen absorb these energies? Well, it doesn't absorb energy until you get about here. And here actually it absorbs 100% of this particular energy, 100% of that particular energy. Notice it totally doesn't do anything with light, visible light, and it totally, this is heat right here. Okay, so now if we switch gears, switch gases to regular oxygen and O3, which is ozone. Notice that these short wavelengths over here, this would be ultraviolet. So with regard to, again, this is absorbance, ABS for absorbance. It actually is great at absorbing those short wavelengths of energy that's coming from the sun. Notice it absorbs a little bit here, visible light, okay, a little bit here, and it does absorb a little bit here in the infrared. We said that variable gases are O3, carbon dioxide, and water vapor. So here is carbon dioxide and water vapor. Now water vapor we do have, isn't this kind of cool how it's kind of hit and miss with these different energies? I'm sure there's a reason for that. Okay, so actually, you know, water vapor does absorb some of those energies. And we said, and remember it's a variable gas, so dry, you know, low humidity, then you're not going to have those absorptions, and higher humidity are going to have those absorptions. And then the last one here is what's the total effect of all of the gases? Okay, so notice that collectively, you know, this would be our shorter wavelengths, shorter lambdas. Okay, and so we're pretty, the window's closed, right? Right there. The window's relatively open here in visible light. We kind of have some peaks throughout here. And notice over here for thermal energy, it's kind of a mixed bag, open, closed. Now before we go on, okay, actually you're going to see in a minute something called SW. That stands for short wave radiation. And guess what LW is? Long wave radiation, exactly. And their cutoff is kind of, I don't know, here between visible light and infrared. But the bottom line, like this says, is with regard to visible light, where we have an open window, and with regard to infrared, we have an open window. Now notice that this window over here for heat is important not only for incoming, but it allows our Earth to vent to outer space. All right, cloud cover. This is one of those practical things I think about sometimes. Clouds can actually have a cooling and a warming effect. And thin, wispy clouds have less of effect either way. Nice, thick clouds basically can be kind of exaggerated either way. And it goes something like this. Obviously, when the sun's out, if you've ever been outside when a cloud went over you, sometimes it feels like the temperature drops like 5 degrees. And then the cloud moves on and the temperature goes back up again. So they can really block sun's energy from getting to you, obviously. So, but you figure that cooling effect only happens when the sun's out. Well, during the daytime. You have a cooling effect during the daytime. Okay. Now, actually, clouds can have a warming effect at night. Okay, so put another way, some of the most bitterly cold nights that I can remember have been nice, clear, crystal clear nights, and it's bitterly cold. Okay, if you have clouds, actually what they can do is as the Earth re-radiates some of the energy it built up during when the sun was out. The clouds act as kind of a blanket, so that kind of reflects some of that infrared radiation back down. So they kind of have both types of effects. So now I want to spend just a minute talking about something that's called the greenhouse effect. And you've probably heard this. I may have mentioned it with carbon dioxide, that we're concerned about the enhanced greenhouse effect. But the way the greenhouse effect got its name is because this is how a greenhouse works. We talked about SW stands for short wave radiation, okay? Short wave radiation actually can go through glass, okay, really good. But once it gets through glass, and this actually happens in your car more than, I don't visit many greenhouses. My car is where I spend some time. So if you've ever gotten your car during the daytime, and my car has black right now on the inside, so in the daytime, that light comes through, it interacts with my upholstery, and my upholstery heats up. So it makes my car warm, but the deal is glass, although glass lets in short wave, it won't let back out infrared. Glass is a pretty good barrier to thermal energy. Okay, so it comes in as visible light, it interacts with your upholstery or whatever's in the greenhouse, and then actually it's converted to IR, infrared radiation, okay, and then it wants to ooze back out, and then you can see up here the glass acts as a barrier. So that's how greenhouses work. So the way it happens then in our atmosphere is, our atmosphere, obviously we don't have a pane of glass, but it's very similar that in a minute I'm going to show you little pictures of water particles. Okay, water particles do this. Carbon dioxide gas particles do this. But basically they are transparent, or they allow that short wave energies to come through, including visible light, but the heat or the infrared radiation that actually the Earth wants to ooze back out, they reflect it back towards the Earth. Okay, so those gases act as glass, kind of in a greenhouse effect. So here we go. There's the sun's radiation coming in, and remember that the geosphere is 80% of the energy it strikes it is absorbed, and it's re-emitted most likely as thermal energy. And so here it is, the thermal energy oozing off of the Earth. And those things that look like little bees or mosquitoes or something, those are actually gas particles. And so anytime you see something that looks like this, kind of a Mickey Mouse, that's actually water. And these are your carbon dioxide particles. So they intercept or react or respond, interact with that infrared radiation. And see, this third figure then is showing them actually scatter that energy, which is infrared radiation, back towards the Earth. So that's how those gas particles act as a blanket. Now, I mean, no, they're not cloud acting as a blanket, but they're gas particles acting as a blanket. So the more carbon dioxide we have in our atmosphere, the more enhanced that effect. Oh, you guys didn't have that one?
It's broken up. You got the first picture taken care of, and the other two are just empty boxes.
I see that now. But my other figure's been okay-ish?
Yeah.
Okay, that's good. I see the wavelength one didn't do it either.
There's one more.
Okay, cool.
Yeah, the EM radiation, the bottom box.
Yeah. We get a little bit of artistry in there anyway. like the next few figures I have are actually from your textbook. And it kind of shows, like, what if you don't have those particles? What does that look like? Okay, so this is what it looks like. So remember I said if you're on the moon during the daytime, you won't have blue skies. So there's obviously no particles to redirect the heat that the moon oozes off. So the moon would be like the geosphere. It would absorb absorb radiation and turn it into thermal radiation, but there it goes into outer space. So this is the Earth again, kind of showing the phenomenon of the greenhouse effect. Okay, so we have energy in, and these would be the particles. Okay, and then last but not least is Venus. So the thing about Venus versus the Earth is Venus has even more, I'm trying to see if they're showing it, it has even more carbon dioxide than the Earth. Our atmosphere is mostly nitrogen, its atmosphere is mostly carbon dioxide. So it has a crazy greenhouse effect that makes its surface temperature, what do we say, the Earth is about 59 degrees Fahrenheit, it's about 941. So, not good. So, this one made sense to me. I looked at it. Let's see if I can do any better with this one. So, if you have 100 units coming from the sun, kind of a typical partly cloudy day, 50 of those units will reach the Earth's surface and be absorbed by the Earth's surface. And then once the Earth's surface absorbs that, actually the Earth's surface is going to conduct and convect, okay? Not as much conduction as convection, but basically it's going to lose about 7 of those units. It's also going to lose 23 of those units it absorbed, 50 units it absorbed by evaporation, latent heat, because we said evaporation requires heat, right? Evaporation requires heat. So actually it's going to rob some of Earth's energy to go ahead and evaporate kind of maybe from the oceans, the large bodies of water. It's going to lose 20 units by just re-radiating it, you know, infrared radiation. Okay, so if you add 7 plus 23 plus 20, you get 50, right? Okay, good. And so as it's being shown here, it gets 50 to the Earth's surface loses 50. So it's kind of a net wash. It's what we call balanced, right? It goes on to kind of show you that of the amount it loses, as far as outgoing radiation, 30 units right away are reflected back to space. 20 units, is that right? Yeah. 20 units are absorbed by clouds, and this is kind of showing this go back up the atmosphere. This gained by clouds is in part re-emitted to the atmosphere. I don't know, I'm kind of lost by the whole thing. I understood it for a while. But this budget is generally balanced. Now, this is just for one location for a given typical cloud cover. But I kind of have to mix that up a little bit in the last slide. Because even though I said it's generally balanced, the only place it's really balanced is, I have it coming up, it's like, is it say 38 degrees latitude? So remember, I could pull the globe up again, find 38 degrees latitude, which I think is south of Florida. Let's see. Here's 30. Well, I guess it goes 15, so here's 30, here's 45, so 38. Oh, it's looking north of Florida. Florida's about, there's 30, so it'd be right about here, maybe. So right about there, throughout the year, the amount of energy it receives is balanced by the amount of energy that it gives up. Aside from that, it's not. So if you are north of that, which we are in what we call an energy deficit. Okay, so we are up here. So that means that actually we lose more energy than we receive. Okay, throughout the year. This is an annual budget. And if you're closer to the equator than 38 degrees latitude north and south, then actually you're in a surplus. So those guys down here actually gain more energy than they release to the atmosphere. So surplus, deficit, and actually a little bit in next week when we meet, we're going to see how the oceans are a pretty good player in kind of helping to relocate warm energy up and return cold energy going towards the equator. So, yay! That's it for tonight.